recording. So, hello everybody. Welcome to the IAMP seminar. As most of you know, this is a bi-weekly event of the International Association of Mathematical Physics. And we are very honored to welcome today Professor Robert Wald, a pioneer of quantum field theory on curved spacetime. I think many of you know him from his famous textbooks, for example, on general relativity. And today he will speak about memory effects, infrared divergences, and scattering theory. Please go ahead, Robert.
Okay, thank you very much. So I assume, and let me know otherwise, that everyone can see the screen, that everyone can see the pointer that I'm pointing to the title of right now, and that people can hear me. And if so, I'll go ahead. So what I'm going to tell you is mainly in this talk is mainly based on this paper that Kartik Prabhu and Gautam Sadaschandran and I put out 2 years ago, on arXiv and published in PhysRevD, but there'll be small parts of this, particularly remarks toward the end, that is work that is still in progress with Dane Danielson and Gautam Sadaschandran. So let me begin by telling you what the gravitational memory effect is. Just to put that on the table and make it clear, this is a physical, potentially observable effect. I mean, suppose we have some array of test particles like I've drawn, initially arrayed in a circle the way I've drawn it. And suppose a gravitational wave is propagating into the screen, that will cause the relative positions of these particles to oscillate into, at leading order, ellipsoidal shapes with axis, in this direction, well, depending on the polarization of the wave, but anyway, in a part cycle of the oscillation, these points will get further apart and these particles will get closer together. And in the next phase of oscillation, these will move further apart and these will move together. The memory, so all this in an asymptotically flat space-time is what's going on at order 1 over r, where the radiation is reaching. The memory effect refers to the fact that after the wave is passed and the space-time has returned to being stationary, these particles won't in general and generically won't return to their original position. So I've shown them being left at late times in this relatively, elliptical kind of relative displacement rather than their circular initial displacement. Now, this is not at all an effect that's special to gravity or anything else. In fact, it's a completely general kind of effect for anything that solves a wave equation in even dimensional space-times, well, where the dimension is high enough that you have radiation for that field. The point is that in d space-time dimensions, radiation falls off as 1 over d over 2 minus 1. Coulombic fields, though, fall off like 1 over d minus 3. Now, it's a completely general phenomena that for solutions of the wave equation, there will be a memory effect in even dimensions at Coulombic order, in the sense that after some burst of radiation, the field at Coulombic order will not, at late retarded times, will not return to its early time value. What is a remarkable accident, though, is that in 4 dimensions, 4 space-time dimensions, these two quantities are both 1 over r. So this basically Coulombic effect gets inextricably intertwined with radiation effects. And as I'll explain now, this is the memory effect is the origin of infrared divergences in quantum field theory. So first of all, I described the gravitational memory effect here initially in terms of how relative positions of test particles, but it's a better idea to use coordinates where the angular positions of these test particles are fixed. And then we're saying that the angular components of the metric don't return to their initial values at asymptotically late retarded times as compared with their initial values. Here, I'm really working at null infinity, and I'm taking here the limit as you go to future timelike infinity along null infinity, and here I'm taking the limit as you go to spatial infinity. So the memory effect, the memory tensor, which is describing the memory effect, is just the difference of the asymptotic values of the angular components of the deviation of the metric from flatness at order 1 over r. And that's also can be written as the integral over all retarded times at future null infinity of the Bondi news, because the Bondi news is just the u derivative of the angular components of the metric. So this follows immediately. Now, as I said, this is nothing special to gravitation, and the analog in electromagnetism would be to look at the vector potential at retarded times at order as a function of retarded time at order 1 over r, and let E be the angular components of the electric field at order 1 over r. And then in analogy to the formulas I have here, the electromagnetic memory would just represent the difference of the angular components of the vector potential at late and early retarded times, which is also equal to the integral of the electric field. And from this formula, you can see that if you have electromagnetic memory, which generically you will in any radiative process, well, this will correspond to, if you had a charged test particle, it would pick up a net momentum kick from the wave that passes by. I mean, so at early times, if your charged test particle was at rest, after the wave has gone by, it will have some momentum kick, so it will be moving then at late times. Okay, so what does this have to do with infrared divergences? Well, that's quite, in fact, simple or straightforward to see. So everything I've said right now is all classical field theory, and what I'm saying here is classical field theory, but the next slide will see what happens in the quantum description. So if we look at the angular components of the perturbed metric, generically, when a burst of radiation goes by, as I've said, it won't return to its initial value. There'll be some offset at late times. Well, if you take the Fourier transform of something that has a step like this, you find that at low frequencies that behaves like 1 over frequency. There's an infrared divergence in that. So if we're now looking at, in the quantum theory, at radiation, but we have some, we want to look at the quantum state corresponding to a classical solution with memory, I mean, a one particle state or maybe a coherent state or something like that? Well, if we're, say, looking for a one particle state corresponding to the positive frequency part of some classical solution that looks like this, that is going to have a 1 over omega divergence in its Fourier transform. Its Klein-Gordon norm that would be used in the one particle Hilbert space, then you can easily see is going to have a logarithmic divergence at low frequencies. So if we try to represent solutions with memory and try to make quantum versions of that, let's say coherent states with memory, try to make coherent states with memory as states in the usual Fock representation, they don't exist because they have infinite norm. There's absolutely nothing wrong with states with memory. They're perfectly legitimate quantum states with memory. They're perfectly legitimate quantum states, but they don't exist as vectors in the usual Fock representation. And if you try to force them into the usual Fock space, then you're going to get divergences when you do that. So this is a situation that, I mean, occurred obviously or came to light in the earliest days of quantum field theory. And, if people are trying to make, predictions for what you'll see at CERN, these things are kind of big nuisances, and they've generally been treated as purely nuisances. And, there are, perfectly good and, in fact, I would claim legitimate ways of working around the fact that the state you're interested in isn't a state in the usual Fock space, but you might want to pretend it is for doing some calculations, like inclusive cross sections or something to predict, what you're going to see in a scattering experiment in CERN, where you're not interested in measuring this very low frequency behavior of the state. So people normally deal with this by putting in some infrared cutoff at very low frequencies to get a state that's in the usual Fock space, then calculate inclusive cross sections where you sum over all the soft photon states that you have allowed with this cutoff that has been put in. And then after you have, computed, these inclusive cross sections, then you can remove the cutoff. And this, again, this works as a practical matter perfectly well for calculating the kinds of quantities that are typically of interest for accelerator experiments, but it's definitely quite unsatisfactory from a fundamental viewpoint, really for two things. First of all, memory is a completely legitimate observable. I mean, people make statements of, oh, you can't observe photons that have such low frequencies. Well, I'm sure you can't observe them with a photodetector, but you could observe them with a test particle that gets a charged test particle that will get a momentum kick. There are a lot of these very soft photons. So it's, this is something that in principle is an observable that might be of interest in experiments other than the typical ones that are being done at CERN. But if you do this kind of procedure, you're not allowed to ask questions about it or analyze it. Even more importantly, though, there's going to be entanglement, and that I'll be talking about that in much of the rest of the talk, of these soft photons or gravitons or whatever. Even if you're not interested in them themselves, they are going to entangle with the hard degrees of freedom that you are interested in. And, one might want to understand what with those, what's going on with respect to that entanglement and decoherence. And then, of course, if you do this kind of thing, you don't have an actual S matrix, you just have a prescription for calculating various quantities. So there has been on the table for more than 50 years now a procedure for constructing Hilbert spaces of in and out states that actually does give you a true S matrix. This is the Faddeev and Kulish construction in the case of quantum electrodynamics with massive charged particles, which is usually described in the language of dressing the charged particles with clouds of soft photons. I'll explain that's really, correlating them with electromagnetic states of memory. And what I'm planning to do in the remainder of the talk is first formulate this Faddeev and Kulish construction in the language of memory and charges associated with memory, or charges really associated with large gauge transformations. The large gauge transformations are closely related to both the memory and these charges that I'll be talking about. But then I want to show or point out that this kind of construction fails if you were doing quantum electrodynamics with massless charged particles. In that case, you can do a similar dressing, but the dressing is so singular that it doesn't give physical states. I will then point out that this kind of construction fails in quantum gravity, and really for a rather different reason. The dressing isn't quite as singular in quantum gravity, but the dressing produces stress energy, effective stress energy and charges on its own and would require its own dressing. And the upshot is that you just simply cannot construct the kind of eigenstates of charges that are needed in the Faddeev-Kulish construction. And finally, I'm going to argue that this whole situation is not satisfactory anyway, even in massive QED, where you can legitimately do the Faddeev and Kulish construction, and that the problem is simply the idealization of scattering from infinity. That's a perfectly good idealization in classical field theory. It's a terrible idealization in quantum field theory, and I think one should not elevate scattering theory to some high position in scattering theory in asymptotically flat space-time to some elevated position in the way one might formulate quantum field theory. Okay, so to begin, let me talk about these large gauge charges first in the electromagnetic case and their connection to memory. So if we do a gauge transformation where the vector potential goes to the gradient of something, but this gradient is now just a function of angle, it's an arbitrary function of angle, this will, the derivative will cause this to fall off like 1 over r, even though the lambda itself doesn't fall off. And this will satisfy all of the, asymptotic conditions one might want to impose on the vector potential. But furthermore, these large gauge transformations are actually not gauge transformations technically from the point of view of, Hamiltonian or Lagrangian theory because they're not actually degeneracies of the symplectic form, the way gauge transformations of this sort, where the lambda goes to zero at infinity, those are degeneracies of the symplectic form. Those need to be factored out of the phase space, and those don't count as states on their own or anything like that. But these large gauge transformations technically do. And an important associated fact is they have non-trivial charges associated with them. And the charge associated with this large gauge transformation at retarded time u at future null infinity is just this integral over the cross-section of null infinity at retarded time u, involving the 1 over r squared part of, well, the electric field. That's more specifically, the 2 is denoting the 1 over r squared part, and the ur are the coordinate components that I'm using, but this is basically the radial component of the electric field. So if lambda were 1, this would be the ordinary charge, but if lambda is some function of angle, this gives, the notion of these large gauge charges. And the difference between the asymptotic large gauge charge at late times at null and future null infinity, so at timelike infinity, minus at early retarded times, that is at space, as you approach space-like infinity along future null infinity, is given by a formula that involves the memory and involves an integral of the flux of charge current through null infinity, which this will be zero if you have massive charged particles. This would be non-zero only if you have massless charged fields present. The charges as you approach the asymptotic future are entirely determined by the Coulomb fields of the massive charged particles. So this is something that is really determined by the matter. This is the electromagnetic memory that I've already referred to. You have a completely similar situation in gravity. If you do BMS transformations, that preserves the asymptotic conditions on the metric, but those correspond to symmetries rather than gauge. And in particular, the super translations are an exact analog of these electromagnetic large gauge transformations. They have non-trivial charges associated with them, where instead of the 1 over r squared part of the radial electric field, you have the 1 over r cubed part of the radial part of the electric part of the Weyl tensor, and you also have this extra term involving the news. And again, the memory effect corresponds to the HAB at late and early times, retarded times differing by a super translation. And in analogy to this formula that I wrote down in electromagnetism, one has a formula that says that the super translation charges at late times, which again are determined by the massive outgoing particles, minus the super translation charges at spatial infinity, is given by a formula that involves the gravitational memory and the flux now of energy that goes out to infinity. But now we will have, even if we don't have any matter at all, just from the gravity itself, we'll get a contribution of the Bondi flux to this formula. Okay, and now a very important thing about these charges that I've just been talking about, and particularly the charges at spatial infinity. Two important points about them. One is that under, well, rather general, although not, I do need the word suitable here because it isn't completely general, asymptotic flatness assumptions. Well, we can look at future null infinity and go to I naught going to the asymptotic past at future null infinity, or we could go to past null infinity and go into the future to get to spatial, limiting to toward spatial infinity. There is a matching of these charges between the in and out charges, both in the electromagnetic and in the gravitational case. So this is the gravitational case here, the electromagnetic case here. When you do an antipodal matching of the, or identification of the two spheres, so these charges map and match, and that's, you know, an important kind of conservation law in some sense in the scattering. But for what I'm going to talk about, the more important point is that the charge at spatial infinity, either in the electromagnetic or the gravitational case, in fact is, well, it's an observable. And in fact, this observable must commute with all gauge invariant local observables for largely the same reason that, you know, the ordinary charge commutes with the ordinary total charge at spatial infinity commutes with all gauge invariant local observables. And that means that the eigensubspaces of these large gauge charges will define superselection sectors of the quantum field theory. Okay, so now let me, well, I'm about to get to the Faddeev and Kulish construction, but let me return to the point that I already alluded to back here when I was pointing out that, you know, states with memory would have infinite Klein-Gordon norm, that there's nothing physically wrong with these states. They just don't belong to the usual Fock space representation. Well, it's not particularly difficult to construct Hilbert space representations of states with memory. So in fact, you can construct such Hilbert space representations of the quantum field algebra by just taking some classical solution with memory, with the desired memory that you want, and, well, going to the usual Fock representation, but replacing the field operator by, sorry, I should have been pointing to this as the classical solution with the memory you want. If you replace the field operator by a multiple of the identity times this classical solution, that will give you another representation of the quantum field algebra. Now, if you did this with a solution that corresponded to a state with finite Klein-Gordon norm, this would give you an equivalent representation. You would just be relabeling what was the vacuum state as now a coherent state associated with this classical solution, and you'd be correspondingly relabeling all the other states, but you wouldn't be changing the theory. But if you did this with a solution with memory, then that doesn't give you, well, that gives you a new representation of the quantum field algebra, where now all of the states in the GNS representation, or all of the state, I guess we're really starting with the usual Fock representation and redefining the field algebra in the way I'm formulating it here. All of the states now in this new representation will have memory delta AB, and this representation thereby that you get of the field algebra is going to be unitarily inequivalent to the original one, but you get this uncountably infinite family of inequivalent representations, all labeled by whatever memory you choose. So you have all of these memory representations at your disposal. And with this background, I can now formulate the Faddeev-Kulish construction. In the case of quantum electrodynamics with massive charged particles. So we first go back to this formula that I wrote down before. When we're dealing with massive charged particles, we don't have any charge flux through null infinity, so we just have this formula, which I've rewritten as a formula for the charge at spatial infinity, as you approach spatial infinity, in terms of the charge at timelike infinity and the memory. But the eigenstates of the charge at timelike infinity, well, there aren't any proper eigenstates, but the improper eigenstates, so to speak, are just the momentum eigenstates of the massive charged particles. As I said, this really only depends on the Coulomb field of the massive charged particles at asymptotically late times, and what their Coulomb field looks like at null infinity just depends on their momentum. So, momentum, states of definite momentum will be states of definite charges here. And what we'd like to do, or what the Faddeev-Kulish construction does, is produce eigenstates of the charge at spatial infinity with eigenvalue 0. And one can do that by taking these improper eigenstates that have some charge at future timelike infinity and pairing them with states of the electromagnetic field that lie in the memory representation, with memory that is equal and opposite to the charges associated with these momentum eigenstates. So if you pair these two together to get 0, then you can take nice wave packet states of these momentum eigenstates paired with these, memory states of the electromagnetic field to produce, things that are wave packet-like in the, charge particle wave functions or whatever, but they are eigenstates, true eigenstates of charge at spatial infinity with 0 eigenvalue. So that gets rid of the superselection problem, because now we're just in one superselection sector. And it also, because of the conservation of this, at least if the charge is 0, as the Faddeev and Kulish construction is making it to be, then charge 0 states in the asymptotic past will evolve to charge 0 states in the future. So the Faddeev-Kulish in and out Hilbert spaces will in fact evolve to each other. So this gives, as I hope I've described, as a satisfactory kind of well, gives a genuine S matrix and gives a mathematically satisfactory kind of description of scattering by working with eigenstates of charge of these large gauge charges of eigenvalue 0, and adding these memory states to which can be of arbitrarily low energy, but they have to have this asymptotic infrared behavior. Adding these states to the states you want to consider of the massive charged particles is what's referred to as dressing the charged particles. Okay, but now I want to point out as I just said, that is a satisfactory way, at least mathematically, of doing scattering in massive QED. I want to point out that this fails if we try to do massless QED in the same way, and it fails for a different reason in nonlinear gravity. So if we're doing massless QED, the Faddeev-Kulish idea would be to again restrict to the sector of vanishing charges at spatial infinity. But now, if I go back to this equation that relates the charges to the memory and the fluxes, now I don't have any massive charged particles, so this term is 0, but I have massless charged particles, so I get a contribution from this flux. And the problem is that, again, the eigenstates of this J will again be momentum eigenstates, just as they were in the massive QED case. But now these momentum eigenstates, so here's a typical momentum eigenstate of n, improper momentum eigenstate of n charged massless particles with 4 momenta k1 through kn. These things now have very bad angular delta. Well, these have angular delta function singularities. That is, these momentum eigenstates, when you compute the corresponding current for that in J, they're all, everything is concentrated just at a point in angle on scri plus or scri minus. For reasons for no good reason, I've switched to scri minus here, talking about the incoming states rather than outgoing states, but the story is exactly the same. This has angular delta function singularities. When you look at what does that mean for the memory, that in fact gives a quite bad angular dependence, angular behavior in the memory. This memory, of course, is is this integral of electric field and is the difference in the vector potential. So I'm going to have bad angular singularities in the vector potential. And those are bad enough that they will result in an infinite electromagnetic energy flux. I mean, even though this is all very low frequency, the angular behavior is bad enough that if you try to do the Faddeev-Kulish construction, the dressing states that you get are all unphysical. This extra sort of bad angular behavior that you get it corresponds to what people refer to as collinear divergences in in massless charged fields, or Yang-Mills fields have similar with the nonlinearity. Now the current produced by the nonlinearities have similar collinear divergences. So this Faddeev-Kulish construction does not work in massive QED. It doesn't work. Yeah.
There's a question in chat about the previous part. This is from Slava Rivkov. And the question is there a canonical way to carry out the Faddeev-Kulish construction, or is there a lot of arbitrariness in how dressing is performed?
Well, this is not a proof that there are no possible ways of doing things. I'm trying to do the Faddeev here. I'm only talking here about doing the Faddeev-Kulish construction in analogy to what's done in massive QED, where you simply dress the charged particles with appropriate memory. Now, the dressing is back here, even in massive QED, is quite arbitrary. You just need to put in photon states that have the right memory. And, you have to put in some photons, but you can make them as low frequency as you want. You have to choose something, but there's a lot of arbitrariness in what you choose in what you use for the dressing. I'm not sure if that is addressing the question that you just relayed to me, but if not,
yes,
feel free for the follow-up question, for there to be a follow-up question.
Thank you.
In the
thanks. This addresses the question.
Okay. Yeah, and in the massless case, one has exactly the same arbitrariness, but whatever you choose, you're going to have these collinear divergences and this problem with infinite electromagnetic flux. Okay, and now what about gravity? Well, there's, in some sense, maybe an even worse problem than gravity, although it's a different problem. If you going back to the electromagnetic case, if you look at the analogous situation in linearized gravity, you kind of have an extra derivative here and so on, and that makes the singularities in the memory milder, the angular singularities. So you actually don't get necessarily, the states are not completely unacceptable. They're still angularly singular, but not in a disastrous way. So you could possibly live with the dressing, but there's a more fundamental problem that occurs here in the gravitational case because of the nonlinearities. Namely, we're looking to try to find eigenstates of the supertranslation charges. Well, we really like eigenvalue 0, but that immediately tells you that there are no states with that property other than the vacuum state. But even if you're just looking for any eigenstate so as to, restrict you to, so when I say an eigenstate, I mean of all of the supertranslation charges simultaneously, that's what you need to restrict to one superselection sector. Again, it's true that the only such state is the vacuum state. I mean, that the proof of that is given in the paper with Prabhu and Sadhishchandran that I gave the reference to at the beginning of the talk. And the basic problem is that this dressing that, you can see why you would run into a problem if we imagine trying to do the Faddeev-Kulish dressing. We can take our hard graviton that has this, flux contribution to the charge at spatial infinity, and we can try to dress it with a memory state. But when we dress it with the memory state, there are going to be gravitons in that memory state. They might be very low energy, but they're not zero energy. When we dress it then with these non-zero energy gravitons, that contributes a little extra to the flux, which messes up the eigenstate property. Well, you might think, okay, let's just dress the dressing and maybe we'll get something convergent, but the direct argument that there are no eigenstates shows that that's not possible. So well, I might as well mention what go kind of in summary of what I've just told you in the last few slides. In the QED case, whether massive or massless, you can just dress the incoming state of definite momentum with photon states of the corresponding memory to get these kinds of Faddeev-Kulish states. That works fine in the massive case. In the massless case, you can do it, but you get these unphysical states due to the bad angular behavior of the photons. But then in quantum gravity, as I've just explained, if you tried to do this, you'd have to dress the incoming gravitons with other gravitons. Those gravitons would then contribute to the flux, and you'd have to try to dress them, and you just can't make that process convergent so that you end up with an eigenstate. Okay, but now I want to, in this very last part of the talk, argue, that the Faddeev-Kulish construction or solution to this scattering issue in massive QED is really not very satisfactory, at least from a physical point of view. Mathematically, there's certainly nothing wrong with it, and that really the fundamental problem just lies in this idealization of scattering from infinity in quantum field theory. So first of all, although you can mathematically construct these Faddeev-Kulish states, they have this, because going back to this formula, there's an infinite degree of entanglement between the incoming massive charged particles and the incoming radiation. It's utterly inconceivable how you could send in a Faddeev-Kulish state from infinity. It is such an entangled state between the radiation and the charged particles. How do you make something like that? It seems impossible physically. So it would certainly be much more realistic to imagine sending in, what you might call bare electron incoming states. That is, send in wave packets of charged particles that are not entangled with the incoming photons. That would be a kind of sensible incoming state, but that runs in then mathematically to the problem that Faddeev-Kulish had to address, these bare electron states, legitimate states, normalized wave packet states, are not eigenstates of the large gauge charges, and they, with respect to any bulk gauge invariant observables, there'll be a complete decoherence of the bare electron into these superselection sectors of the large gauge charges. but those are just momentum eigenstates. So if you imagine sending in a bare electron, by the time it got to the bulk, and of course it gets to the bulk as soon as it leaves null infinity, so it doesn't really take a lot of time in some sense to get to the bulk, but by the time it gets to the bulk, it's completely decohered into momentum eigenstates, which means that the state is physically translation invariant, space-time translation invariant. There is no state, well, no state with aside from the vacuum state, but here we're talking about a state, let's say, with non-zero charge. There's finite but non-zero charge. There is no state that's translation invariant. So what I'm saying here is that if you can mathematically consider a bare electron incoming wave packet state from null infinity, there is no physical state in the bulk that describes. I mean, you kind of have to use Faddeev-Kulish states for that reason. These are the ones that are so entangled in the asymptotic past that when they get to the bulk, they get, they become physically reasonable states. So it's instructive, I think, to think about, what would happen if we have an electron, in the bulk, we have some electron in a trap and release it. I mean, shouldn't that, look like a bare electron at infinity or something like that? I mean, we don't have this electron is kind of not initially, dressed with a cloud of soft photons or whatever. Okay, let me not ramble on in that direction. Let's just think about what happens if we have an electron in a trap and we release it and allow it to propagate freely to infinity. Well, I claim what's going to happen is that this electron is going to decohere into momentum eigenstates. The longer it propagates, the more entangled it will become with soft radiation that is associated with its initial release. When we release the electron, there will necessarily be some radiation created, but the Fourier transform of that radiation, if we consider what happens over all time, will contain arbitrarily low frequencies. And the electron, as it propagates, will become more and more entangled with this soft radiation. And if you take the asymptotic limit to infinity, it will be completely decohered. So why don't we find things like this when we do laboratory experiments with electrons that seem to maintain its coherence? Well, if you look at the nature of this effect, the decoherence is occurring only logarithmically in time. And in any finite time required to do a real experiment, and this decoherence is a completely negligible effect. So the punchline of what I'm trying to say here is that if you release an electron and make it a free electron in your laboratory and let it propagate out toward infinity, if you look at the late times relevant to a practical experiment, you go far away to a far away part of your laboratory and look at the electron, reaching the apparatus far away in your laboratory. That's extremely different from what is actually going to happen at infinitely late times to this electron. At infinitely late times, it will completely decohere into momentum eigenstates. But at the late times of some practical experiment, that effect will be completely negligible. So what I'm getting at is that this idealization of scattering from infinity is not a very sensible idealization, from the point of view of practical experimental physics. That contrasts with the situation in classical field theory. I mean, it's certainly very useful to take limits to infinity, and the limit at infinity does really, in the classical case, I'm claiming, describe give a good description of the behavior of fields at large but finite times that are relevant to real experiments and observations. But that is not the case I'm arguing and asserting, in quantum field theory in 4 dimensions with a massless field, because you're going to get this logarithmic growth of entanglement of the charged particle, if we're doing the electromagnetic case, with the kind of what you might refer to as the soft modes of the massive field. And although this logarithmic growth is completely negligible this decoherence effect is completely negligible in laboratory experiments, it is infinite in the asymptotic limit. So what I'm saying is, in quantum field theory in 4 dimensions with a massless field, the behavior of states at asymptotic infinity is very different from the behavior of states at large but finite times in an experiment. Now, this is not of what I'm saying here is not of any consequence for the kinds of practical calculations that I alluded to in the beginning, where one is, obtaining inclusive cross sections at given 4 momenta. The calculations there are correctly describing behavior at finite times relevant to experiments. It's the situations where you're sending in wave packets, not plane waves, not idealized plane waves, but wave packets from infinity, where you're going to get these decoherence effects. And if one wishes to elevate scattering from infinity to a fundamental status in the formulation of the theory, I think these, issues that I've raised and hopefully elucidated to some degree, I think really need to be taken into account. And, my view is that one should not elevate scattering from infinity to some fundamental status in the formulation of quantum field theory in at least 4 dimensions when you have a massless field around. Okay, thank you.
Thank you very much for this interesting talk. Now there is time for questions, so please just unmute yourself and ask.
I have a question. Hi, Bob. This is Ted Jacobson.
Hi. Yeah, hi.
Thank you for that talk. My question is about what sets the scale of the logarithm that you referred to in terms of the growth of decoherence, like if I imagine the electron released from a trap.
Yeah. Right. So if it's log t, it must be log t over, some other time scale. That would be, at least in the back of the envelope calculations that, we've done, that would be the time scale over which the electron is released from the trap. So, if so I mean, I'm referring to this sort of case where the electron is getting more and more entangled as time goes on with the soft modes, but the entanglement is increasing only logarithmically. There would be some time scale associated with releasing the wave packet. I mean, if you released it instantaneously, there'd be some, singular behavior associated with the instantaneous release. So I'm imagining that we're releasing it over some time scale.
Okay, so suppose I wanted to push this and, design an experiment that would detect this effect. Could you describe what would be required? Like, what's the best experiment to detect it? Or is it, like, in principle impossible to detect it? It didn't sound like you were saying that.
No, I don't think it certainly shouldn't be impossible in principle to detect it, but this this would be a much smaller effect than things like wave packet spreading and so on when one has released it. I would have to think about that a little bit more. I mean, I'm trying to remember in these back of the envelope calculations, I don't really remember, and I would hesitate to try to reproduce on the fly, some of the numbers. But I mean, one of the things I recall we looked at is, if you wanted to take an electron, put it in a superposition, separate them and then collide them together at how far. Of course, that depends on the velocity at which you're going to send them in to each other. I mean, this would be like doing an accelerator experiment, but one that would show the coherence or lack thereof. How far would you have to separate them, and given the velocity that you would be sending them in against, and it's clear if you put in any kind of ordinary accelerator dimensions or something, this is the decoherence that you get from the soft radiation is a very negligible effect. I think that's not answering your question very well, but what I am asserting is, yes, this should be possible in principle to measure, but it's such a tiny effect that I can't imagine it actually being measured. A tiny effect in a realistic experiment.
Yeah, okay, thanks. Maybe in the future I can hear about the specifically what would be required.
Yeah.
Okay, any other questions or remarks?
I have a question, Jan Derezinski. You mentioned that in the case of gravitation, one should dress the dressing and again dress the dressing and so on. Does it follow from the nonlinearity of gravitation, or is it true also in linearized gravitation?
No, it's entirely the nonlinearity of gravity that I'm talking about. You wouldn't have, if you did linearized gravity with massless, with a massless matter field, you could dress the flux of the massless matter field at infinity with gravitons, and if you then neglected the nonlinear effects of gravity so that there wasn't any Bondi flux associated with the gravitons, you'd be okay.
Oh, okay. Yeah, one does not know how to quantize nonlinear gravity anyway, so yeah. Okay, thank you.
Yeah, I have a question.
Yes.
Yes, I have a question.
Yeah.
So I think if you want to compare the quantum field theory of gravity, maybe electromagnetic theory is not the best example, but QCD, which is also nonlinear. So now, if you look at QCD, you see some of the problems that you mentioned in some sense disappear due to asymptotic freedom and other phenomena. So in other words, in QCD, the scattering will not, no one will try to do the scattering using gluons and quarks as the asymptotic states. It doesn't make sense. So scattering is between asymptotic states, and in the asymptotic states, you don't see color, for example. So I think maybe one should compare to QCD to see how this kind of arguments go through.
Yeah, we did in the paper. I mean, just in the paper that I referred to, we did look at Yang-Mills theory, not QCD, but kind of imagining that we had asymptotically free states of the Yang-Mills field and could do scattering theory with them. But just looking at that's okay. Where am I here? So not necessarily taking that theory that seriously as describing nature, but one can talk about these the large gauge charges and so on in the Yang-Mills case, and memory in the Yang-Mills case, and then from the nonlinearities of the Yang-Mills theory, you get a current flux. So we did look at that case, and there that you still get the bad collinear divergences, so you get this singular behavior, but you also have more of a problem. Well, you can't construct the Faddeev-Kulish states. It is possible you could construct eigenstates of zero charge, zero large gauge charges, but not enough states of those, it would appear, to do scattering theory or define scattering theory. So anyway, we did to some degree do something along the lines that you're suggesting, and that does, at least mathematically, raise, that does give this nonlinear color charge current flux and things like that into the theory that makes an interesting comparison between the massless QED and the gravitational case. But
can I ask a question, Slava Rychkov?
Yes.
So as you explained, so you explained this connection between the memory effect and the infrared divergences, which is interesting. And as you said, in particle physics, we normally compute inclusive cross-sections, and then the infrared divergences go away.
Well, I don't know that they go away, but you manage to ignore them. Yeah.
Well, that's not the way I would put it. I mean, that's really, people have reached good physical understanding of why this is a reasonable thing to do. I wouldn't.
And I completely agree with that.
People definitely corresponds to what people measure. But what I wanted to ask is that, okay, it's a theorem that they go away, that once you sum over in states and out states, sometimes you only need to sum over out states within the certain window. And it's a theorem to prove. It's not a very hard theorem, but it's a theorem which requires a proof. Bloch-Nortzig theorem and KLN theorem. And I was just wondering if your connection with the memory effect allows to shed an additional light on why this procedure works, why infrared divergences go away, because normally this requires an interesting interplay between real emission processes and loop effects. So it's not fully trivial that divergences cancel. So does memory effect shed any light on why they cancel?
Yeah, I mean, off the top of my head, I wouldn't. I would say no, or at least not. Nothing kind of that I can think of, and and as I hope I made clear, I mean, there's the inclusive cross-section type calculations I think are completely justified and correct and all that. It's just, you're not really doing S matrix type scattering. You're really constructing an algorithm for computing cross sections and so on, but you're not really saying what in states go to what out states, and you're not looking at decoherence effects between different momenta, because the calculations are all being done with improper momentum eigenstates and so on. I mean, but to your direct question was, does one get further insight into why that works from, using the ideas from memory and large gauge charges? And off the top of my head, I don't see how that, gives some new insight into this, though I haven't really thought about it.
Mm-hmm. Mm-hmm. Thank you.
Can I ask a question? This is David Bridges.
Please go ahead.
This is David Bridges. I want to return to the first question about the time scale in the logarithm for decoherence. Is this, in some sense, the same thing as saying that it's the time it takes for the electron, which I take it is massless in this case, to travel the length of its own wave packet, something like that?
Let's see. What I was talking about here, I was talking about an ordinary massive electron. I mean,
I misunderstood because I thought that we were in the context of massless particles.
No, but I returned to massive QED in the previous slide.
Okay. Well, even better, because in that case, I'll ask my question again, because I was a little worried that you can't localize a massless wave packet. But is it, I don't really understand what a releasing from a trap means. Can I just look at the resulting wave packet of that process and just say how long it takes to travel the length of its own wave packet would be the characteristic time in this logarithm?
No, well, okay. Yeah, no, I mean, the characteristic time certainly has to do with how much radiation is associated with this release. So I don't think it would be directly related to timescales, like, like travel time across the wave packet, or how much, it really is an effect of entangling with very low frequency radiation that results from the release.
I see. I was thinking that the meaning of taking a very long time to release the wave packet would be to reduce the amount of radiation that is created.
Well, so that will. I mean, the it's
the question then is
time over the release time or something. I mean, this is very rough back of the envelope stuff, so don't take any of this too literally or whatever, but that is giving an idea. But the important thing is logarithm, which means that this does not become, even if you wait a billion times more than it took to release the electron, you're not getting a huge effect. I mean, the coefficient in front of the logarithm is very small in the first place. So,
okay.
Okay, then maybe let me ask a question, following up on the last question about this electron released from the trap, and the question if we will see interference patterns, or if we wait sufficiently long, maybe we should see decoherence.
yeah.
So there is an alternative approach of Buchholz and Roberts to infrared problems, who basically say if we restrict our space-time from Minkowski to the future light cone, then the problem should disappear. So presumably on a future light cone, it would be difficult or impossible to compute these memory effects in this idealized form of an integral from -infinity to plus infinity, and then you couldn't read off from the memory effects the momenta, and there would be no reason for decoherence no matter how long you wait. Don't you think so?
I mean, so what I've written on this slide, I'm asserting, I mean, haven't done any calculations other than very rough back of the envelope type things, but that, you release an electron wave packet and it really will completely decohere into momentum eigenstates. It's just going to take a hell of a long time for that to happen, but it really is going to do that. And that's not, that really is an effect. It really does get entangled with this soft radiation. So I think this is a genuine physical effect that, would occur if you could allow this electron to just propagate freely forever, and it really was in an asymptotically flat space-time and all that.
Yeah, then it's still strange that after 100 years of experiments, nobody noticed that this interference.
It's not, but this is something that 100 years is way too. I mean, again, I need to put in the numbers. If you did one experiment for 100 years, that isn't anywhere near long enough.
I see. Okay.
To this effect.
I see. Okay.
That's what I'm arguing.
Okay. Any other questions or remarks? Does not seem to be the case. So maybe let's thank Bob again and turn to the informal part of the meeting. So I am stopping the recording.